All right. It's all over. So today we'll just talk exam review. If you got a question along the way, just throw it out there. I'll try to do my best to answer it on the fly if you come up with something, okay? The exam is pretty much set, almost fully written. I'm going to tell you that it's not as easy as exam 2. There's some easy ones. There's some not. But the format's going to be the same. So, room assignments, this is just on Canvas that I'm showing here, guys. If you go to... Okay, well, this mouse button doesn't work. If you went to our course Canvas page, you went down to the bottom, the last module in the home page is final exam, and the only thing there is room assignments. So those of you guys who are taking the regular exam, that's already showing up in your course schedule. Those of you who are taking the McBurney exam, same time, different room, 2239 Engineering Hall. So that's listed here. The rest of you guys, you got to hike up to Humanities, 7:45 a.m. I've gotten quite a few emails asking for an alternate exam time, and I believe in shared suffering. If, like most of you, have to sit through a 7:45 a.m. exam on a Saturday, you all got to do it. So I'm not offering a second one. That's it. If you got 3 exams on the same day, try to move your other ones. So sorry. Okay? That's how I feel about that. I know, it's brutal. Okay. Other things. Preps has not totally locked in yet, but they are shooting for Thursday, the 16th at noon. And that's as much as I've gotten from them. Location TBD. So hopefully they'll get back to me and they will let me know. Any preps people in the room right now? You have a room?
My instructor said they were thinking 1227 hall.
Should I not even write that down yet?
He said it was a soft maybe.
A soft maybe? Okay. So we got a soft maybe so far, so we're going to leave it at Thursday at noon. And you guys will get back to me later today or tomorrow or before Thursday at noon, hopefully. Okay. The format, still going to be 3 questions with the idea of these questions each taking a half an hour, but it's a final, so you got a 2-hour block. So maybe that'll just allow you to suffer for an extra 30, or you'll actually be able to get some more work done. Either way, we're not changing the format too much. It's still going to be 3 questions. All right. Just like before, 3 questions, kind of like homework problems. No short answer, none of that business. So we're going to focus on the last chapters, 6, 7, 8, and there's no 9. 6, 7, and 8. The chapter 6 stuff I'll tell you, this is where we're dealing with velocity and acceleration analyses. There's not going to be a problem dedicated only to this. All the stuff that you have to do from chapter 6 is going to filter into these other questions. So the stuff that you got to do from chapter 7, which is Newton-Euler for rigid bodies, and then chapter 8, which we had 2 topics, work energy and momentum. So these are the things I expect you to know. Oh, the last thing I threw on there, right at the bottom, is sneaky. Moments of inertia. So now that these things are rigid bodies, we don't care about just tracking a point. We got to care about that whole shape. And we're worried about rotation. We always think that moment of inertia is like something's resistance to rotating. So how far is that mass spread away from the point it wants to rotate about? What you should be able to do moments of inertia-wise is come up with the moment of inertia for a composite system based on the table, or actually what's in the note sheet is just a list. It says a disk, a thin rod about its CG. So if you got you know a disc. You've got a thin rod. You've got, I don't know, a rectangle. You've got a point mass. If it's pinned about some point that it's going to be rotating around, kind of everything we learned for our Newton-Euler, sum of moments about 0.0. Hey, that was easy. We can relate that to moment of inertia about 0.0 times alpha. If we had a pinned about 0.0, hey, that made life easy for work energy. We're taking half I-O omega squared. Same thing for momentum. If I'm looking at momentum and I got a body that's pinned and this whole thing is rotating, now I'm looking at my moments about 0.0. So very often, if I've got this body pinned at some location, you should feel comfortable writing this moment of inertia, right? So if I shortcut this, the whole system about O. We got the rod plus the disc plus the rectangle, all about 0.0 plus the point mass. So to find the whole thing, you can look at all of these independently. Let's look at the rod. So for the rod, this guy, our little table will tell us its moment of inertia about its CG. 1/12 ml squared, right? But we got to shift that down to 0.0 plus the parallel axis shift, mass times how far am I shifting? L over 2 squared. One-third ml squared. This is the one that's not on the equation sheet that I expect you to know and that I'm more than happy if you just jump to. The moment of inertia of a rod about its endpoint is 1/3 ml squared. So it's not on there. You guys are smart. Disc, same thing. We're taking this. It's moment of inertia about its CG. We're shifting it down. The rectangle, hey, the moment of inertia about its CG. Whoop. And its parallel axis shift is this. Here for the rod, mass times half length. The rectangle, whatever the mass of the rectangle is, times how far do we shift it? So the point mass, well, how do we deal with this? Moment of inertia about a point mass about its CG. It's infinitesimally small. It's just a point. So as it rotates, like, hey, all that mass is at one specific point. This is 0. So all that a point mass has is its parallel axis shift plus mass of the point mass times whatever this is, d sub point mass. Okay, add them all up, parallel axis shift. We pretty comfortable with that? No need for me to do those two? Good. All right. So chapter 6 stuff. What did we do? This one was no forces, no moments, none of that business. All we looked at was velocities and accelerations for rigid bodies. We used the vector method, and we used another method that we said was taking the derivative of geometric constraints. So the vector method, maybe we had some goofy system, A, B, C, D. And it's pinned at A and D. So we used the vector method. Maybe we were given something down here, omega AB. But we wanted to find out what's going on up here. So if we were given something like this, we used the vector method to kind of inch our way along with what we knew. The key parts of the vector method were writing equations for the various rigid bodies. So if we look at velocity in particular, I have the velocity at point B is my velocity at point A plus angular velocity of that body crossed with the vector between them from A to B. Right? So we could write a velocity at any old point on this rigid body, but remember, for this equation, it's just going to be this rigid body. And I happen to pick the endpoint B. For these shared points, we want to write multiple equations. So if we write one equation from here, we want to write another equation for this body, BC. Then we'll have two equations for the velocity of B. So for the other rigid body, velocity of B, and I write that with respect to velocity of C. Or maybe I need to write it with respect to the CG location if I want to figure out energy and how this thing's translating at its center of gravity, right? So now I got the angular velocity of BC crossed with the vector from C to B. Every time we got these joints, we're thinking about adding more equations. One for each rigid body. What you don't want to do is get yourself into trouble and write the velocity of C with respect to the velocity of A. Because A and C aren't on the same rigid body. There's two pieces there. So, what would you choose as your omega? Maybe there would be an instance where you could say that, hey, A is the instantaneous center and this would work. But in general, we need to be on the same rigid body. Okay? Everything that's true for velocity with this rigid body technique is true for acceleration. The whole way we're doing this is we're trying to write multiple equations for the points that are connected. I like to think of it as coming from one direction, write everything I know. I come to a roadblock, then I write the other direction, write everything I know, come to a roadblock. Hopefully we can get some answer of what's in between. So remember, I guess we'll just look at this. If you're doing the acceleration, you might as well do velocity first because you got these omega terms in there anyways. Most likely you're going to need to do velocity analysis to solve for the terms used in acceleration. And then also what I got on the board here, for this class, 2D planar motion, 2D, this is minus omega squared r, where omega is now just a scalar, and the r is still the vector. So this is 2D planar motion. Everything we're doing here, though. We had an offshoot of the vector method, or a little special case of the vector method, where we looked at the instantaneous center for zero velocity. We came up with 4 cases in class. The nice part is you don't need to use this. It's just a shortcut if your eyeball is clever enough to pick out one of these cases. If that's the case, awesome. Use it. If it's not the case, hey, just crank through with your vector approach if that's what it takes. For this drawing that I've got here, I kind of try to draw these guys parallel. Let's pretend like these are parallel lines. Right? So if this was the case, I got this pin body. This is traveling a circular path. I'd have my velocity of b. This is a pin body, circular path. I'd have my velocity of c. And then we think about how we drew the instantaneous center. We looked at the point we cared about. We had our velocity vector, and we drew the line perpendicular to our velocity vector through that point. So perpendicular, perpendicular. And this is one of the useful cases. Here we have these perpendicular lines are parallel, so they'll never intersect and give us a location of an instantaneous center. So if they're parallel and they'll never intersect, here I could write that omega bc was 0. Because this rigid body, for these two velocities, this thing is just translating at this point. This body is not rotating at all. I could change this orientation just a tiny bit, and this wouldn't be true. But for this case, for this drawing that's perfectly parallel, that's how it's going to move. There's other cases ranging in their level of usefulness. Go and take a review of that and see if you want to use them. All right. Quickly, the method we did describe here, well, actually, all this vector business that we've talked about is for one particular instant in time, a snapshot, like this is the picture, this is how the velocities and angular velocities are related. Same with acceleration. So this is only true for a given drawing or at a given time. If you needed something that was true in general, that's where we use our differentiation of our geometric constraints. And I think the one that we probably used was maybe we had a wall with a ladder leaning against it, right? And here, we could relate this position x to this angle theta. Sines and cosines, that's all we're doing, right? Here, x is equal to L cos theta. If we wanted to then take and find the angular velocity of our ladder, or the velocity at the bottom of our ladder, we've got position. Let's just take time derivatives. One derivative in time, x dot. Derivative of cosine is minus sine, right? Minus L sine theta, theta dot. Second derivative, get you to acceleration. This is great because it's going to be true for all angles theta if you've written it right. So you've got one body to track. You can write a relationship between how these various variables relate, and you need a function for the whole time, or the whole array of positions. You got to go this route. If I start giving you some crazy mechanism that's got like 4 pieces together, and you think, I bet he's trying to make me relate sine of theta to phi to alpha to beta, like, I'm not, right? Like, it's going to get really big and really nasty really fast. So small, easier problems. Hey, this is great. Gives you way more information because it gives you something in general. This, when the going gets tough, and maybe you're just trying to figure out the max acceleration or the acceleration at various points or velocity at various points. This is kind of the fallback technique. All right. So getting on, like, the first two things we talked about, moments of inertia, velocity and acceleration analyses, know that stuff. That's your setup for your big 3 questions, right? Like, that's the things you're going to need to know to get you there. So when we have left is 3 tools. We've got Newton-Euler, F equals ma, and sum of moments equals I something alpha, right? Depending on what you pick for your moments. Newton-Euler. We've got work energy. We've got momentum. I'm going to give you one of each of these questions. If you are super stubborn, all you need is Newton-Euler, right? F equals ma, sum of moments. You can solve any of the questions I'm asking with this. It may not be the easiest way, but you can do it. Work energy and momentum, these are our shortcuts. So Newton-Euler, let me write that. Can solve them all. Solves all problems. Right? Great to know. Work energy, this is when we're relating speed, which could be velocity or angular velocity, omega, and position. That could be a displacement x or an angle, theta. Could put a y in there too, right? So what do we do? For work energy, we started with F equals ma, and we integrated this over a distance. So we've integrated force over a distance. So I integrate acceleration, I get velocity information. Integrate over position, that's why I've got position stuff here, right? So if you're given a question that asks you specifically about speed and position, how fast is this ball rolling when it gets to the bottom of this hill? Bing, work energy. Momentum. We've taken F equals ma, and we've integrated this with respect to time. So instead of getting position, now we've got velocity. I use velocity here instead of speed because this is a vector now. I care. So it might be v and omega, and we got time. I'm pushing on this or pulling on this or spinning on this. How fast is it spinning after 3 seconds? Hey, momentum. Velocity and time, speed and position. Everything. So when I say it can solve everything, also is our only tool for solving some things. And that's kind of what we want to get at. So this is good for speed and position. This is good for velocity and time. This is F equals ma. So if we need accelerations, that might be A or alphas. It's going to be a good tool to use. If we need reaction forces, think about work energy. Think about a reaction force, something that's like pinned. Like, hey, there's a force there, but work energy, think about all the terms you got. You got kinetic energy, you got potential energy, and you've got this work term, but that work term really only relates forces that are moving over some displacement. So if it's a force that's at a reaction, that's pinned, like you're not going to be able to use work energy to get yourself there. So if you need accelerations, you need reaction forces. If you need to know what forces look like as a function of something over time or position, maybe this would be a better technique to use. When you think of trying to force your Newton-Euler to solve these other guys, well, if we have time, we'll look at an example problem. But think of what you naturally get from a Newton-Euler. Hey, I've got some springs. I get acceleration as a function of x. Or alpha as a function of theta, right? So if I want to get position or I want to get to time, I've got to do some fanciness to work on my acceleration. Right? If I want to get this, you probably remember we did a lot of like goofy chain rule stuff back in chapter 2 that you guys didn't like based on your exam 1 performance. Right? So if we had acceleration in its simplest form, definition is dv dt, but it's a function of x. We got to do this. Dx over dx. And we said dx with respect to dt, that's velocity. This guy, I'm going to shift it over. So a of x dx is equal to v dv. Hey, now I can get to velocity. But you think about the work you're doing to get there. That's pretty tricky. Or if I need to get to position, I need to take another integration of that to get to position. So you can do it. But I mean, you might be talking like a 3-page solution versus a 3-line solution, right? It can be that drastic of a difference. So what I want you guys to do, knowing full well that we wrote 3 exam questions for you to solve in 3 ways, I want you to open that exam and say, what is he asking me to do? Oh, this one is speed and position. Work energy. You turn the page, don't even solve it. You read the question. What is this one asking me to do? He wants to know the velocity after 3 seconds. Velocity and time. Momentum. What's the last one? Oh, he's asking for accelerations or some forces. Newton-Euler, right? Make life easy on yourself. Figure out what we think is the simplest way to solve these problems and go about it. It may not be that stark of a difference. It might not be 3 pages, 3 lines. But there is kind of a flow to things. So try to figure out your roadmap. Once you've got your roadmap of which one you want to do, then you'll follow the steps for those various techniques, right? So F equals ma. The translation part's great. It's the same. All we're doing now is we're tracking the center of gravity, right? So same thing we did in chapter 3 for particles. We draw FBDs. So Newton-Euler, what do we do? Step 1, FBD. Put all those external forces on it. Maybe you've got reaction forces that you need to keep. Maybe you've got 2 bodies that you need to split up. You know, maybe there's a cable going from this one to this one, and it's operating over a pulley. So maybe you draw a free body diagram of this first piece. You draw a free body diagram of this second piece. 2 separate free body diagrams, split apart, right? 2 sets of sum of forces equations, 2 sets of sum of moments equations. So you draw your free body diagrams. Set these equal to your kinetic diagram. I'll try to perfectly redraw my blob. That's this one. So with our kinetic diagrams, they're interesting now. 3 chapters ago, everything was happening through the CG. Well, I guess we still had it kind of interesting because we looked at what coordinate system we're using. So that still matters. But now, mass times acceleration in x. Mass times acceleration in y. But this also has the decisions you got to make. Where am I going to be summing my moments about? Should be included on your kinetic diagram. Hey, Sonny hates us. He's making us do them about point P. Right? Like, hey, now you need to have this vector because your moments equation has this term, r from P to G, that's what I've just drawn here, crossed with the acceleration of G. So your acceleration of G is ax and ay, right? Plus, I would draw this guy on there, I sub G alpha. Now when you're writing your equations, you know, like, hey, I haven't forgotten anything. We're not leaving anything out. We've written all the pieces down. There's a reason I drew this vector. Let's keep track of everything. So this was our case that was totally general. If I had moments about P, you see what I got here? My sum of moments about any old point P, off in space, not on the body, translating, accelerating. I've got Ig alpha plus R cross MA. And my R is from P to G. Always true, right? We didn't use it all that often, though. More often than not, we looked at the special cases where this simplified somewhat. If we had a point O on the rigid body that we were looking at, this equation changes a little bit. And the little bit that it changes is if that body's on point O, I'm no longer looking at my acceleration at G and my moment of inertia with respect to G. I'm looking at them with respect to O. So that can be easier depending on your setup. So the ones that are you really get your money's worth, though, the bottom two. You could drop out this whole second term, this whole R cross MA term. If we're lucky enough to have a rigid body that's pinned at a location on that body, now O is pinned, think, well, if O is pinned, this acceleration of O term would drop away, right? So now we're just going to be left with some moments about O is IO alpha. Or if we look at our general case for point P, if P was G, our second term drops out because we have a vector from G to G then. So when you start looking at these problems, and you know it's the Newton-Euler problem, you got to figure out where do I want to take my moments about. Immediately you think, can I be lazy, and am I lucky enough to have this thing pinned somewhere on the rigid body? If yes, absolutely take your moments about that point. You don't have to. You're free to do it the hard way. But my recommendation would take them out at point O. If it's not pinned on the body, and that body moves, it's free to go wherever it wants, look at the center of gravity. That also makes your life easier. Hopefully there, you're like, oh, okay, I don't have to track that extra term. That's good. But if it brings in a whole bunch of extra forces and a bunch of hard angles to calculate your moments from, maybe that's not worth it. And you do pick some random point P off in space. So try to be clever. Try to use these two simple cases first. If you fall back and you can't use these, then work your way up. Instead of starting with a general case and just picking some point that you have randomly assigned. So make sure we can't use the easy one before you start using the hard ones. Oh, I'm going slow here. All right, roll without slip. So if you're determining between roll with slip and roll without slip, we've kind of got the same a procedure we'll use. For these bodies, we're always going to assume first roll without slip. And the reason we do that is because at the end of the day, we have a check we can make. We roll without slip, and then we see if our frictional force, so it's F, force of friction, or maybe I go like this. If that's less than the static friction coefficient times n. If anyone downloaded or printed these notes more than 3 hours ago, you got an error here. So I had kinetic here accidentally. So fix that if you have old notes. So that's our check. We're going to assume roll without slip, and we get some bang for our buck if we assume roll without slip. So if we roll without slip, we have an acceleration at our center of gravity, and we can relate that to alpha of the body. Because it's not slipping, as the center is translating, we know it's rotating. So we can do this for velocity, and we can do this for acceleration. How do we come up with this? This is our CG. This was our point A. We said that, hey, if point A is rolling without slip, the acceleration at A in the tangential direction has to be 0. Because what's happening with the bottom of that wheel and what's happening with the ground, they're kind of linked up in that tangential direction. In the normal direction, all bets are off. We have a normal acceleration from this thing, change in direction. The fact that it's rotating. That's your omega squared r term. So what we get for roll without slip is our acceleration at our CG is equal to minus alpha r. And I guess the way I've drawn this as a vector, it's in the I direction. So why minus alpha? Right-handed coordinate system, positive k direction would be counterclockwise. So we're rolling this way with a positive k. So if we want to roll with a positive x acceleration, we need a negative alpha. You want to convince yourself of this? Write out acceleration of your CG is the acceleration of A plus alpha cross r from A to the CG minus omega squared r from A to the CG. That's going to pop out. That's all the answer is, right? Same thing for velocity. Velocity of the CG minus omega r. That's important when you're doing momentum and work energy problems, because you're always looking for velocities. So when you're solving these roll without slip problems, this is the great piece of information you get. And this is also same thing, roll without slip. You set up your problem, you write sum of forces, sum of moments, maybe I'll do this about G. Your free body diagram, your kinetic diagram, now you can link up these two terms because it's roll without slip. You can solve for this frictional force acting at the bottom. You do your check. If it's less than static friction times n, awesome, you're done. Turn the page, roll without slip is right. If you don't get that case, F is force of friction is greater than mu k times n. Uh-oh. That means you needed a greater force to maintain that roll without slip condition. So if this is the case, then AX does not equal minus alpha r. You lose a piece of information. Oh no, not linked anymore. But you gain the fact that the force of friction is the kinetic friction coefficient times n. We know exactly what our kinetic friction force is if it's slipping. If this thing's rolling without slip, you don't know what that friction force is. You just know that it's less than static friction times n. It could be 0, it can be a tiny, tiny bit, and it could be all the way as big as the static friction coefficient. You have a question?
You just answered my question. I was going to say, was your mu k supposed to be
Yeah. Sure. No one saw that. Okay? So, if this is the case, this is an S. Thank you. You go back, and you think, oh, I got to do all that work again, but now I'll do it. No, you don't have to do much more work. You just have to go back in here, undo this link between these two guys, substitute in the force you have. You've already got the free body diagram right. You've already got the kinetic diagram right. You're just going to have to go punch your calculator one more time to figure out the new numbers. Okay? One other gotcha is that when you write these frictional forces, so let me muddy this up and put a force on here. If you write your frictional forces from your sum of forces equations, and you go and you solve it, and you get a number out of it, and that frictional force is negative, no big deal. It just means you drew it in the wrong direction, right? So you can either keep it negative, or you can flip the sign of your arrow around and take a positive value. It doesn't matter for the static case. Once you get to kinetic and sliding, because you've already assigned its magnitude, you better damn well have that direction right. Otherwise, it's doing the opposite of what you want. So this is maybe a nice check. Like, hey, I drew this force of friction wrong. So when I looked at it with respect to the static friction coefficient, it was some negative value, but it was bigger. Oh, negative. Flip that sign around so that when you have to then use it in your kinetic friction, you'll at least have the direction pointing in the right way. Okay? So roll without slip. Long story short, always, always, always start with no slip. Prove yourself right or wrong. All right. Yeah.
Was there something where like the direction of friction changes depending on whether it's slip or without slip?
Is there something that the direction of friction can change if it was with or without slip? Not in like a... Yeah, I think you could probably come up with a contrived case of that. And maybe it would depend on, like I just drew this, say this wheel rotating. This wheel could be rotating in different directions, right? It could be, like I could say we are spinning in reverse, yet we're going this way. So your friction force would oppose that motion. But I could be spinning forward, like a burnout, while going this way slowly. Then my friction would be in the opposite direction. So how would your static friction compare to that? That might be a little sneaky. You might have to do some convincing of yourself. What way is this bottom point moving relative to the ground? All right, work energy. So we talked about it already. Speed and position. Once you've identified something as a work energy problem, do yourself a favor. Write out our work energy relationship. T1 plus V1 plus our work, non-conservative, is T2 plus V2. Start setting up your various components. Hey, my T's, half mv of g squared plus half ig omega squared. So for each rigid body, we're tracking the velocity of its CG and the rotation, angular velocity omega. Right? If we're lucky enough to have a fixed axis rotation, we can relate our velocity of g and our omega together for fixed axis. And these would just become I-O omega squared. So we have a fixed axis O. This was pretty much the new part. Right? Everything else was the same. For springs, that's potential energy, half k delta squared. Hey, we also threw in torsional springs now that we're worried about things rotating. Torsional spring constant times theta squared. Our potential energy from gravity, totally the same. Now we're just tracking the CG location, right? MGH. All you got to do is figure out what point you want to track. Make life easy on yourselves. You got state 1 and state 2. Pick one of them as your datum so you can make that gravity term fall away on one side or the other. Then you just have to track one. So, work energy principle, the work that we're doing from non-conservative forces, typically for us, friction. Maybe we've got external forces pushing, external forces torquing now with moment. So we can also equal from states 1 to state 2 sum of moments d theta, right? So force over a distance, torque over an angle. That's what we're doing here. All right, last one, momentum. In the linear sense, we didn't really do much for rigid bodies versus what we did for particles. Linear momentum was still P1 plus our impulse, which was the integral of force dt, is equal to P2. With these P's are linear momentums. Mass times the velocity of the CG. That's the only difference. It's like now we're tracking a particular point on that body. It's got to be the CG. So for us, what do we got to worry about? If you draw your FBD, but you've identified this as a momentum problem, hey, think about all the different forces acting on your body. These are what we're going to integrate over time, right? So you're integrating all these forces acting on the body. And remember that this is a vector. So you might have an x equation, you might have a y equation, if that makes it easier for you to split up. Angular momentum, that was the new one. So we could take our angular momentum about any old point P. So our angular momentum about that point, Ig omega. For us, if it's some random point P, we got to have this correction term. A vector from P to G crossed with mass times the velocity of the point we're tracking. So this was our general case for angular momentum. We said we want to use this angular momentum impulse principle, but we need this to be true first. We need the time derivative of our angular momentum is our moments. Actually, I got this minus the velocity at P crossed with mass times the velocity at G. To use our angular momentum impulse principle, we want to pick G such, or pick our point P such that the second term falls out. So we could do that if point P was fixed, velocity would be 0. If point G was fixed, velocity is 0. If the velocities were parallel, or if point P was G, right? Anything we could do to make the second term go away. So if the second term can go away, we can then use our impulse momentum principle, which was derived from taking the integral of this. We get the angular momentum at 1 plus the integral of moment with respect to time is equal to our angular momentum at state 2. In general, this is what our angular momentum looked like. We also looked at special cases to make this look a little easier. So we said, what if I'm taking moments about my CG, angular momentum about my CG? So this vector r from G to G would fall out. Then my angular momentum would only be Ig omega. If we have a pinned location on the rigid body, now my angular momentum I-O times omega. So we're always going to try to use one of these locations if that's possible for angular momentum. If I'm trying to do an angular momentum problem, I'm looking at the CG first, or pinned location on the body first. If I can get away with that, it makes the rest of these solve a little bit easier. Okay, I am out of time. You guys are dismissed. Good luck, study hard. All right.